In this section, we're going to go back and we're going to talk about limits, but about limits in a specific form. For example, a limit of the form x approaches c of a quotient f of x divided by g of x. A limit like this. And let's say that when we take the limit as x approaches c of the numerator and the limit as x approaches c of the denominator, we end up getting one of the following indeterminate forms. For example, imagine that we get 0 over 0, or let's say infinity over infinity. In chapter 2, whenever we had limits tending to one of these indeterminate forms, we couldn't conclude anything about the limits. We didn't know whether the limit was going to exist or not. In fact, what we had to do was to engage in some sort of algebraic manipulation, hoping to cancel factors out. And then when we tried taking the limit a second time, then in many occasions we would get a real number, in which case the limit existed, or we would get that the limit tended to positive or negative infinity. But that meant that we had to do quite a bit of algebra, and sometimes that was not easy. It was quite tedious, and there are situations where the given function, the given quotient, may just be too difficult to explore algebraically. Luckily, however, now that we know about derivatives, maybe we can take advantage of that and somehow use derivatives to evaluate limits. And this is what actually L'Hopital's rule will tell us. L'Hopital will tell us that it will show us how to explore a limit of a quotient that tends to an indeterminate form, such as 0 over 0 or infinity over infinity. But it's going to tell us how to explore the limit using derivatives. Let's go ahead now and see what the rule is telling us. This will be our first theorem. Suppose that f and g are differentiable functions. Differentiable functions in an interval I. Okay. And let C be a number in that interval I. So C is any number in I. Suppose that g prime of x is not equal to 0 in I, except possibly at C. In other words, we don't mind if the derivative of g is equal to 0 at C. What we want is for the derivative to be non-zero around C. We're talking about limits, and limits, these are concepts about neighborhoods. We don't care exactly what happens at C. We care about what happens around it. And around it, we want for the derivative of g to be non-zero. So if these two initial conditions are satisfied, then this is now what L'Hopital's is saying. Number one, if, let's say, the limit as x approaches c of the numerator is equal to the limit as x approaches c of the denominator, and let's say that these two limits are equal to 0. This is exactly what generates the indeterminate form 0 over 0. If this is the case, then L'Hopital says that the limit as x approaches c of the original quotient f of x over g of x is going to be equal to the limit as x approaches c of the quotient of the derivative of f divided by the derivative of g of x. That's what it says. It says that the limit that we are trying to find, the limit of f of x over g of x, will be identical to the limit of the derivative of f over the derivative of g. So if we get that this limit is equal to L or to plus or negative infinity, then that means that the same conclusion will be true for the original limit that we were given. But again, something very important to notice here is that when we differentiate, we're not going to use the quotient rule just because we have a quotient as a function. We are going to find the derivative of the top by itself and then the derivative of the bottom by itself. And if this limit, now the limit of the derivatives, exists and is equal to L or to positive or negative infinity, then this conclusion will be the same for the original limit that we had. The second way in which we can use L'Hopital's rule is by generating the following indeterminate form. Let's say that we have the following. If the limit as x approaches c of the numerator, so of f of x, is equal to the limit as x approaches c of the denominator, g of x, and this is equal to plus or minus infinity. This is actually how we get the indeterminate form, infinity over infinity. If this is the case, then again the rule says that the limit as x approaches c of f of x over g of x is going to be equal to the limit as x approaches c of f prime of x over g prime of x. And same idea as before. If the limit of the quotient of the derivatives is equal to L or to plus or minus infinity, then the same will be true for our original limit. In conclusion, we are going to use L'Hopital's rule to try to evaluate a limit of a quotient. So as long as the function in the numerator and the function in the denominator are both differentiable in some interval I, and as long as the derivative of the denominator is not equal to 0 around c, then L'Hopital says that if we get a limit with this indeterminate form, let's say 0 over 0, or a limit with this other indeterminate form, infinity over infinity, then the way that we can try to evaluate that limit is by considering the limit of the quotient of the derivatives. If we find the derivative of f, the derivative of g, and that limit exists, maybe is equal to L, or maybe we get that is equal to plus or minus infinity, then this conclusion will be the same for the limit that we were given, the original limit. So the limit of the quotient of the derivatives is equal to the limit of f of x over g of x. Let's look at example 1. Example 1 is asking us to find the following limits. And this is the limit as x approaches 1 of the natural logarithm of x over x minus 1. Well, I have to make sure that I identify my two functions. In this case, for example, the numerator is f of x and the denominator is g of x. I want you to quickly notice that f of x and g of x are differentiable in their domains. The natural logarithm is differentiable for all x values bigger than 0, and the denominator x minus 1 is differentiable for all real numbers. So then when I consider both of them together, I can claim right here that f and g are differentiable in the interval from 0 to positive infinity. And I want to make a note here that 1 is in this interval from 0 to positive infinity. I also want us to note that the derivative of the denominator is equal to 1. So then that is really showing that g prime of x is not equal to 0 around 1. So we will say here that g prime of x is not equal to 0 around x equals 1. So then with this, we are now ready to see if we have an indeterminate form for this limit. If we get an indeterminate form of 0 over 0 or infinity over infinity, then we know that we can apply L'Hopital's rule. So let's see what is happening here. The limit as x approaches 1 of the natural logarithm of x is equal to 0, and the limit as x approaches 1 of x minus 1 is equal to 1 minus 1, which is also equal to 0. This shows that we are generating the indeterminate form of 0 over 0. That means that we can apply L'Hopital's rule to try to find the value of this limit. So then that implies that the limit as x approaches 1 of the natural logarithm of x divided by x minus 1 will be equal to the limit as x approaches 1. And now we're going to differentiate the numerator. The derivative of the numerator is 1 divided by x, and the derivative of the denominator, which happens to be 1. So this will be equal to the limit as x approaches 1 of 1 over x, which is going to be equal to 1 over 1, which is just 1. So then this is telling us, therefore, this is saying that the limit as x approaches 1 of the original quotient will be equal to 1. Part B is asking us to find this limit, the limit as x goes to 0 of sine x minus x in the numerator and x squared in the denominator. So before we use L'Hopital's rule, we're going to make sure that we identify f of x and g of x. The numerator is f of x. The denominator is going to be g of x. So then, condition number 1, let us note that f and g are differentiable. And they are differentiable pretty much everywhere within the real numbers. So for all x in negative infinity, positive infinity. I want us to notice, obviously, then that 0 is going to be in this interval right here, right? So 0 is in there. Then we will note that the derivative of the denominator, which is 2x, is not equal to 0 around 0. So g prime of x, which is 2x, is equal to 0 only when x is equal to 0. But what we care is for it to be non-zero around 0. So I'm going to make a note of that. I am going to say that indeed g prime of x is not equal to 0 around x equals 0. So now that these two preliminary conditions are satisfied, I can try to see whether I get an indeterminate form of 0 over 0 or infinity over infinity. So let's see what happens to the limit of the numerator and the limit of the denominator. So third investigation, the limit as x approaches 0 of sine x minus x. This is going to be equal to the sine of 0 minus 0, which is 0. And then we're going to look at the limit as x approaches 0 of x squared, which is just equal to 0. And this now give us the indeterminate form of 0 over 0. So then L'Hopital's rule says that the limit as x approaches 0 of sine x minus x over x squared is going to be equal to the limit as x approaches 0 of the derivative of the top. So that's going to be cosine of x minus 1 divided by the derivative of the bottom, which is just 2x. And if I now try to plug in 0 for x, I am going to have cosine of 0 minus 1 over 0. 2 times 0 is 0, which is going to give us 1 minus 1 on top over 0, 0 over 0. And this is showing that we get, again, an indeterminate form of 0 over 0. So then it is possible to use L'Hopital's rule a second time around. Perfectly possible. This time you will consider this to be your f of x, and you will consider 2x to be your g of x. And then you're going to check the conditions again, but this time I am just going to be a little bit more informal. Notice that both the numerator and denominator are differentiable everywhere within the real numbers. I also want you to notice that the denominator, 2x, is such that its derivative is non-zero pretty much everywhere this time, because the derivative of 2x is 2, which is just a constant, is non-zero. So then that means that because I get the indeterminate form of 0 over 0, I can go ahead and try to apply L'Hopital's rule once again. So what I am going to do is, from here, I am going to continue by differentiating the top and the bottom. So this will be equal to the limit as x approaches 0. The derivative of the numerator is going to be negative sine x. The derivative of minus 1 will be 0. And this will be divided by the derivative of 2x, which is 2. And then when I try now substituting 0, I am going to get negative sine of 0 divided by 2. That will be negative 0 over 2, which is equal to 0. So then you see that now we did get an actual value for the limit, which shows that it is okay to use L'Hopital's rules twice. Sometimes you use it the first time, and if you get an indeterminate form and all of the conditions are satisfied, then you can use L'Hopital's a second time around. Part C here is asking us to evaluate the limit as x goes to 0 of this function. Now, as a quick check to see whether I will need to use L'Hopital's rule, if I just quickly plug 0 into x and 0 over here, 0 and 0, I am going to get that the numerator tends to 0 and the denominator tends to 0 as well. So it seems as if the entire expression tends to the indeterminate form of 0 over 0. This gives me a hint that I should try to see if I can apply L'Hopital's rule. So now though, as soon as I realize that I may have to use L'Hopital's, then I have to be a little bit more careful and make sure that the two conditions of L'Hopital's rules are satisfied. So I am going to make this as just as before. The top is going to be f of x, and then the bottom right here is going to be my g of x function. And then I can see that f of x is practically differentiable around 0. In a small neighborhood around 0, the numerator is perfectly differentiable. Same thing with the denominator. Around 0, g of x is differentiable. So then I know that condition 1 is satisfied. If you don't mind, I am going to avoid writing those conditions just to speed up the process. So f and g are differentiables in a small interval around 0. Now I have to check the second condition. I have to check that g prime of x is not equal to 0 around 0. However, given that g of x is equal to x squared times tangent of x, that makes it a little bit difficult for me to see whether indeed that derivative is non-zero. Also, when we try to apply L'Hopital's rule and we end up having to differentiate the denominator, because I'm going to have to use the product rule, I am afraid that things are going to get a little bit messy. So what we're going to do is the following. Before we rush to differentiating, we're going to go ahead and re-express tangent as sine over cosine. And the same thing over here, sine over cosine. We will do a little bit of simple algebra and we will re-express this original function in a different but simpler way, in a different form. We're going to kind of simplify it for sure. And then we're going to be able to see the conditions of L'Hopital's more carefully, and we should be able to differentiate in an easier manner. Let's go ahead and do that. Let me change all the tangents to sine x over the cosine of x minus sine x. Then this is going to be divided by x squared times sine of x divided by cosine of x. Then I'm going to go ahead and get a common denominator in the numerator. So I'm going to multiply top and bottom by cosine of x in the second term. That is going to give us the limit as x approaches 0 of, we're going to have the main division here. The denominator of the numerator will be cosine of x. And then on top, we're going to have sine x minus sine of x times cosine of x. And then here in the denominator, we will have x squared times sine x divided by cosine of x. Then we're going to take this division and turn it into multiplication by multiplying the numerator times the reciprocal of the denominator. So that is going to be equal to the limit as x approaches 0 of sine of x minus sine x times cosine of x. All this divided by cosine of x. And let's do the reciprocal in a different color. So times cosine of x. So practically flipping the denominator. Divided by x squared times the sine of x. Then we can nicely cancel cosines over here. And then if I actually factor sine from the numerator, I am going to have sine x times 1 minus cosine of x. All this will be divided by x squared times sine x. And then again, I'll be able to cancel sine. And I am going to now have that this is equal to the limit as x approaches 0 of 1 minus cosine of x over x squared. So I want you to notice that now we have something that it's a little bit simpler to analyze. Now let's try to analyze the limit. If I just quickly do a check to see if I'll need L'Hopital's rule, let me just briefly plug in, and I do this mentally. I plug in 0 for x in the numerator and 0 for x in the denominator. And I'm going to get 1 minus cosine of 0, which is 1. So 1 minus 1. I'm going to get 0 on top and 0 below. So that is telling me that so far this is giving me an indeterminate form of 0 over 0. So I do feel that, yeah, I'm going to have to apply L'Hopital's. So then again, the numerator plays the role of f of x. The denominator is my g of x. And then notice that both f and g are perfectly differentiable around 0. And I want you to notice that now our denominator is considerably simpler than what we had here at the very beginning. My denominator here is x squared. The derivative of x squared is 2x. I know that 2x is non-zero to the left of 0 and to the right of 0. So it's non-zero around 0. That satisfies the second condition. That means that I can go ahead now and see what happens. So let me continue over here. I am going to quickly show that the limit as x approaches 0 of 1 minus cosine of x is going to be equal to 1 minus cosine of 0, 1 minus 1, 0. The denominator, the limit as x approaches 0 of x squared, that is equal to 0. So then again, the top and the bottom, when put together, will tend to 0 over 0. That's the indeterminate form. So then I know that I can go ahead and apply L'Hopital's rule. So we know then, I'm going to start from the very beginning. The original limit that I was given was the limit as x approaches 0 of the tangent of x minus the sine of x divided by x squared times the tangent of x. That we came and we re-expressed as the limit as x goes to 0 of 1 minus cosine of x divided by x squared. And now applying L'Hopital's rule, this will be equal to the limit as x approaches 0. The derivative of 1 is 0 and the derivative of cosine is negative sine x. So then 0 minus negative sine x divided by the derivative of x squared, which is 2x. So this will be equal to the limit as x approaches 0 of sine x divided by 2x. And now what I am going to do is to take this practically 1/2, right? I have here sine x over 2x. So I can take 1/2 and place that in front of my limit. So 1/2 times the limit as x goes to 0 of sine x divided by x. And I hope that you remember that this limit is equal to 1. That means we have 1/2 times 1, and 1/2 becomes the value of the limit of this function. Part D is giving us another limit. It's asking us to evaluate the limit as x goes to 0 of this function right here. If I quickly try to plug in 0, 0, and 0 for every single x, I'm going to get that the top tends to 0 and the bottom over here also tends to 0. So this is telling me that pretty much the entire quotient is approaching an indeterminate form of 0 over 0, meaning that we may have to use L'Hopital's rule. So then I have to check my two conditions of L'Hopital's. Again, if I denote the numerator as f of x and the denominator as g of x, I can immediately see that around 0, f is differentiable and g is differentiable. I also notice that since g of x is equal to x to the third, g prime of x is going to be 3x squared. And 3x squared is non-zero around 0. So I satisfy the conditions of L'Hopital's rule. In fact, now, just quickly checking now that I get the indeterminate form, I'm going to show here that indeed the limit as x approaches 0 of the numerator, tangent of x minus x, is going to be equal to tangent of 0 minus 0, which is going to be 0, and the limit as x approaches 0 of the denominator, x to the third, is going to be equal to 0. So then this is showing that indeed this limit gives me the indeterminate form 0 over 0. So then that means that I am ready to apply L'Hopital's rule. I'm going to start by differentiating the numerator. The derivative of tangent is secant squared x minus 1 divided by the derivative of the denominator, which is just 3x squared. Now, something that I want us to notice here is that in the numerator, I can use an identity. If you remember, and I'm putting this as a side note over here, we know that 1 plus tangent squared x is equal to secant squared x. If I now subtract 1 and bring that to the other side, that means that tangent squared x is equal to secant squared x minus 1. That is telling me that this entire expression can be replaced with tangent squared x if I want to. In fact, this is exactly what I'm going to do next. I'm going to take this and say that the limit as x approaches 0, the numerator will be re-expressed as tangent squared x, and this will be divided by 3x squared. So what I really have right now is 1/3. I'm going to bring the 1/3 in front of the limit, and I'm going to have here the limit as x approaches 0 of tangent squared x divided by x squared. When I get to this limit, then if I do a quick check by plugging 0 for x on top and 0 for x below, again, I seem to get an indeterminate form. So this is kind of telling me that I may have to reapply L'Hopital's rule. So I am going to go ahead and I am going to let the top be f of x, the bottom be my new g of x, and I'm going to quickly check the conditions of L'Hopital's. I want you to notice that f and g are both differentiable around 0. I want you to notice that the derivative of g, so the derivative of x squared is 2x, and 2x is non-zero around 0. So then I can apply L'Hopital's rule. Now, if I want to be really careful, I have to quickly show here that the limit as x approaches 0 of tangent squared x is equal to 0, and the limit as x approaches 0 of x squared is also equal to 0. And this is exactly what is giving me the indeterminate form 0 over 0. So then I'm going to go ahead and proceed with L'Hopital's rule a second time. I'm going to take the derivative of the numerator. Remember that you can rewrite the numerator as tangent of x, all of that squared. And then in order to find the derivative of tangent x squared, we just have to use here the chain rule. So then this will be 2 times tangent of x times the derivative of the inner function. So times the derivative of tangent, which is secant squared of x. And all of this will be divided by the derivative of x squared, which is simply 2x. Then we are going to cancel these 2 over here, and this is now going to give us 1/3 times the limit as x approaches 0 of tangent of x times the secant of squared x divided by x. Now in my next step, I am going to separate this product. I am going to put tangent and x together and secant squared by itself. So we're going to have 1/3 times the limit as x approaches 0 of secant squared x times the limit as x approaches 0 of tangent of x over x. I haven't changed anything, I just reorganized the factors. Now I think that I am ready to do my substitution here. If you remember that the secant squared of 0 is a valid number, is a valid real number. Secant squared of 0 is actually equal to 1. So that's going to be noted in my next step. And then I am going to have here times the limit as x approaches 0 of tangent of x divided by x. So again, this over here is equal to 1. And when I continue right here, let me separate these two. I am going to have 1/3 times 1 times the limit as x approaches 0 of tangent of x divided by x. And then, believe it or not, I can apply L'Hopital's again. If I do a quick substitution of 0, I'm going to get tangent of 0, which is 0 over 0. So I can think of my numerator as my new f of x, the denominator as my new g of x. I can quickly show that the limit as x approaches 0 of tangent of x is equal to 0, and the limit as x approaches 0 of x is equal to 0, and this is giving me the indeterminate form of 0 over 0. So I can now have 1/3 times the limit as x goes to 0 of the numerator, which is secant squared of x divided by 1. And then that will give me 1/3 times the secant squared of 0, which is going to be 1/3 times 1, which is going to give me 1/3 as the value of the limit. Okay, so this is a great example of sometimes applying L'Hopital's rule 3 different times. Part E is giving us a one-sided limit and is asking us to evaluate this limit. What is really nice to realize here is that if this limit tends to an indeterminate form, 0 over 0, or infinity over infinity, I can still use L'Hopital's rule. I can use it in the same way that I have been using it in the previous problems. In fact, the rule is identical, so I don't even have to restate it, because if I do that, I will be stating the same theorem. So what I'm going to do here is I'm going to try to solve this problem, and you're going to see indeed that the steps are identical. So with one-sided limits, as long as they tend to an indeterminate form, you can apply L'Hopital's rule. So let's check the indeterminacy here. The limit as x approaches 0 from the right of the numerator. In the numerator, we have cotangent. I'm just going to informally here, or roughly, draw the part of cotangent around 0. If you remember, cotangent looks like this, something like that. So then you notice that as x approaches 0 from the right, cotangent tends to positive infinity. So then I can say here that the numerator tends towards positive infinity. And then when I look at the natural logarithm looks like this as well. So then you notice that as x approaches 0 from the right, the y values of the natural logarithm are going towards negative infinity. So then the bottom is going towards negative infinity. And this is now giving me a hint that I have an indeterminate form. In other words, I should be able to apply L'Hopital's rule. So then, in order to do that, we're going to go ahead and let the top be f of x, And we're going to let the bottom right here be g of x, just as before. I'm going to quickly, informally here, just verbally, I am going to check that f, so cotangent, and the natural logarithm are differentiable in a small opening, in a small interval around 0. So in other words, if I consider, let me go back to my graph over here. If I consider this tiny interval to the right of 0 and this tiny interval here to the right of 0, I know that f and g are nicely differentiable around 0 to the right of 0. Then I'm going to go ahead and look at the derivative of the denominator. Well, that is pretty easy. We can even do it mentally here. If you notice, the denominator is the natural logarithm. The derivative of the natural logarithm is 1 over x. So again, 1 over x is non-zero around 0. Just quickly sketching 1 over x. 1 over x looks like this on the right side and like this on the left side. So you can really notice that in a small neighborhood around 0, especially to the right of 0 over here, the derivative is not equal to 0, is non-zero. So then that means that the first two conditions of the theorems are satisfied. Now, all that I have to show is that I have one of the indeterminate forms. So I'm going to go ahead and do that here on the side. I am going to consider the limit as x approaches 0 from the right of cotangent of x. And by looking at the graph over here, again, we know that this limit is equal to positive infinity. And we're going to look at the limit as x approaches 0 from the right of the denominator, the natural logarithm. When you look at the graph over here, the limit approaches negative infinity. So then all of a sudden, when we put these two together, what we end up getting is the case of infinity over negative infinity. Now, we don't really care about this negative. We just care about the infinity over infinity, and that's your indeterminate form. Now we are ready to start differentiating. So moving to the left here, this will be equal to the limit as x approaches 0 from the right. The derivative of cotangent is negative cosecant squared of x divided by 1 over x. Then this is going to give us here the limit as x approaches 0 from the right of negative cosecant squared x times x. What I will do right now is to take this negative in front of the limit, and I will re-express cosecant squared as 1 over sine squared x. That means that we're going to have x over the sine squared of x. Now here, if I try to plug in 0 again for x, I am going to get another indeterminate form. So then that means that we should be able to apply L'Hopital's rule a second time around. So a quick check again. This is my new f of x. This is my new g of x. And then I notice that both x and sine squared x are differentiable to the right of 0. And then we also notice that sine squared of x is non-zero in a neighborhood to the right of 0. And I'm saying to the right of 0 because we are approaching 0 from the right of 0. So if those two conditions are satisfied, we're going to go ahead and check that the indeterminate form is present. So we're going to consider the limit as x approaches 0 from the right of x. That is going to be equal to 0. And the limit as x approaches 0 from the right of sine squared x, that is going to be equal to 0. So then we end up getting the indeterminate form of 0 over 0. So I am ready to proceed here with L'Hopital's rule a second time. This will be equal to minus the limit as x approaches 0 from the right, the derivative of the numerator is 1, and in the denominator, we're going to use chain rule. So then that means 2 times sine x times the derivative of sine, which is cosine of x. I am hoping now that you noticed that we can apply an identity to the denominator. The denominator is equal to the sine of 2x. And now, if I look at my denominator, you're going to notice that as x approaches 0 from the right, I'm going to make a note of this here, and this is just a note. I'm going to note here that as x approaches 0 from the right, sine of 2x approaches 0 as well. So this is really telling us that 1 over the sine of 2x is going to get very, very large. So it's going to approach pretty much infinity. So this will be approaching here positive infinity. Again, the idea that if the denominator is approaching something very, very small, 1 over something very, very small is something very, very large. So now, continuing here, we will say that the limit will approach pretty much negative infinity. Because again, this 1 over sine of 2x approaches infinity. And if you remember, there was a negative right here. So this negative is right here in front of infinity. So the entire limit is going to approach negative infinity.